Now we'll see B tree deletions. So far we have seen B plus tree deletions and we understand them. In the same way we can do B tree deletions, but there is a small difference. I will show you what is the difference. So example, this is order 3 B tree and minimum number of keys are 1, maximum number of keys are 2. We can calculate using that formula, right? Now in this case, so first of all we deal with case number 1. You are deleting a key from leaf. Then what happens? Second one we deal with case 2, which is let's say deletion in internal node. Whenever you are deleting from internal node, what happens? We deal with two cases one by one. First of all, we start with deletion in leaf. So whenever you are deleting a key from leaf, example let's say 18, then minimum is 1, right? Then after deleting 18 also we have sufficient keys, then there will not be any problem, then we don't do anything. So this is the way we delete keys in leaf. Okay, but sometimes what happens, so when you delete a key, like example when you delete from this node 25, then this node will have 0 keys, but that is a violation of minimum condition, then we should do something. So we will discuss now how to delete 25. If I delete 25, so obviously like B plus tree, go for borrowing. So you have only one sibling, ask that sibling, Mr. Sibling number 1, please give, otherwise please share the keys or please transfer the keys. So but always we should do that borrowing through the through the parent. So 32 should go here, see here, it was 25, right? So when it is 25, then send 32 to this side. In the place of 30 I write 32 and in the place of 25 I write 30. In that way if I transfer the key through parent, then it would be fine. See now 32 is left 30, 32 is right is, see here 32, but in B tree we don't repeat the keys, right? We should delete it. Since we have sufficient keys here, there will not be any problem. But sometimes what happens, here you will not have sufficient keys from where you are transferring the keys. Example, let's say deletion of 30. Now we will see deletion of 30. So case I can say we have seen two cases now. In deletion of leaf, case number 1, you are deleting a key but we have sufficient keys, quite easy. Second one, you are deleting a key that doesn't have sufficient keys, that means underflow is going to occur, then we borrow from the neighbors or siblings. So if it is successful, then we do that. Sometimes it may not be possible, that is case number 3 I can say. So that is example, let's say you are deleting 30. So now this node doesn't have sufficient keys, then we have to ask sibling doesn't have sufficient keys. If you, after moving, if you delete a key value from here, that's why what to do then the only possibility like B plus tree, merge. Whenever you merge these two nodes, it will become 30 and 34, but in B plus tree we simply deleted this key. But here we should not do that because 32 is very important key for me. 32 has two duties. One is anchoring, second one it has some record pointer. So if you simply delete 32, then you can't access 32. Really 32 is part of your file. We can't delete it here. So remaining things are only 30 to 34. Let's summarize. There was 30 comma 34, right? So it is 32. Now this was separate, this was separate. Whenever you delete 30, then this node will not have sufficient keys, it violates minimum condition, then go try to transfer the keys from sibling, but that is not possible, then go for merging. So whenever you go for merging, pull 32 and of course we have deleted 30, we don't include 30, we should not also. So you get like this, we should remove 32 from here, right? So now 35 is left is 32, 34, 35 is right is 38, 39. Now 2 pointers and 1 key, perfect. Now we'll try to do this again. Let's delete, so now let me write it clearly, this is 32, 34. Let's delete 32, sufficient keys, no problem. Delete 34, not sufficient keys, then transfer the keys from this one, borrowing. Borrowing will work because this node has more than sufficient keys, that's why it will work, but we have to transfer through the parent. So what is the parent? 35. So we do like this, Mr. 35, go right side. Then you create an empty space, Mr. 38, please fill it. And I delete here. That is what we do, borrowing. So borrowing sometimes may not work. At this moment it's working, right? Let's do it again. So delete 34. When you delete 34, no problem. It has sufficient keys. Now delete 35. If you delete 35, So problem, it doesn't have sufficient keys after deletion, then we can't go for borrowing because even this is also having minimum keys. So the only strategy is simply merging. Now this is the time to merge. So 35 and 39 if I merge, already I told you 35 and 39, but of course 35 is going to be deleted, right? So we have to pull 38. Sometimes, example, you have a big tree like this. How this process we should do, I will tell you. Example, you have a big tree like this with, let's say, two keys, something like this, A comma B, here something C, something D comma E. And let's say minimum condition is 2. Here minimum condition 1, right? If minimum condition is 2 and you are deleting, let's say A. When A is deleted, violation of minimum condition, then we have to try for borrowing. Borrowing will not work because even this node has only two keys. Then go for merging. Whenever you go for merging, remaining keys of node 1 and all the keys of node 2 will be merged. That means other than A, everything will be merged. So it will form B comma D comma E node, but we have to pull C in between. That is what the strategy. So B, C, D, E will be the key. Node. Similarly here, we should do the same. So when you do that, so 38 has to be, 38 has to be removed from here, correct? And we have to pull here. Then you get this one. So only 0 keys and 1 pointer, 38, 39. But the problem is now this node, don't worry. This node doesn't have sufficient keys. So internal node is now violating the minimum key condition. Sometimes it happens. Remember, whenever you are deleting from leaf, then you go for merging sometimes. Whenever you merge, we are pulling one key from the root or some next level. Whenever you pull a key from next level, then that the next level, whatever you are talking about, from which you are pulling the key. Example, this key you are pulling to lower level, right? Then this internal node may have this violation of min key condition, correct? So here it is happening now. There was one key, so it was satisfying min key condition. Now there is no key. When there is no key, then what we have to do? Let's think about it. So the rule is, the strategy is like this. Whenever it has a problem, do the same. What you do is just try to borrow from siblings. So that is what we do. Let's do that. So we try to borrow from, but borrowing will not work. See, 15. Can we take 15 to here? No. The reason, even it is also having only one key. So borrowing will not work. When borrowing will not work, then we go for merging. So that's why we have to merge these two internal nodes. Let me merge these two internal nodes. Then this will be the story, right? You will have like this 15, and but there are 3 pointers, right? 1, 2, 3. Correct? But whenever you do merging, we know one thing. What is that? We always pull the anchor, correct? So that is what, because why we have to pull, I will tell you the two reasons. One is, initially you have two keys now, 10 comma 20, then 3 pointers. But when you merge these two nodes, this 20's need is there is no need, right? So that's why I can say that we should pull 20. So if you pull 20 to here, then what happens? Node will be merged. You get 3 pointers. 15's left 12. In between 15 20, we have to attach this one. The right side of 20 will be this one. So finally, we have solved the problem. We started at deleting at key, leaf. Then that error propagated to internal nodes, and we adjusted that also. Now let me summarize it. So first of all, case number 1, deletion in leaf. Whenever you are deleting from leaf, then if that leaf has sufficient keys, that means more than sufficient keys, then nothing to do. Sometimes what happens, so that internal leaf node may not have sufficient keys. That means exactly it has minimum number of keys. When you delete, then it will have some insufficiency. Whenever it has insufficiency, strategy number 1, borrowing. I already explained you. So through parent, if borrowing doesn't work, sometimes it doesn't work, then what to do? Merge these two nodes by pulling the anchor in between. That is always the strategy in B tree. But in B plus tree, we delete that anchor, correct? That's the difference. Now let's do it again and again so that you get an experience. Deletion in leaf. So far this is your tree, right? I would like to delete something called 12. Let's delete 12. Whenever I delete 12, then we have first strategy number 1. So is it violating the minimum condition? Yes, it is violating. Then go for borrowing. So borrowing through anchor, 17 will go here and 15 will come here, that's it. Then delete 17. Now delete 15. When I delete 15, then what happens? Insufficient keys in this node. Then we should go for borrowing, but borrowing cannot work. The reason it has insufficient keys after borrowing. That's why what we have to do, merging. So whenever you merge, then it will be like this. We have to pull the anchor. Let me merge these two nodes first of all. Then pull this 17. So all the remaining keys of first node in this problem, especially 0, but in bigger trees you will have remaining keys, right? When you delete a key, maybe other keys may present in that node. All that plus 17 plus 18. 17 is an anchor. So we should remove from this one. So now resulting node will have now in this problem only one key, then 2 pointers. So perfectly the anchoring will work. 20's left is this one, 20's right is this one. In that way we can do it, right? Let's keep continuing. Example, let's say I am deleting 17. Is there any problem? No, sufficient case. Now delete 18. What to do? Borrowing, correct? So borrowing will work. Mr. 38, go to the root, parent. Mr. Parent, come to this one. 20 here and 38 here, and 38 is actually deleted from leaf. It is like deleting from this leaf, but it has sufficient keys, there will not be any problem. See, perfect so far. Now delete 20. Whenever you delete 20, insufficient keys, then borrowing will not work, then go for merging. All the remaining keys, simply add like this. All the remaining keys of this node, all the keys of this node, and along with anchor in between. So it will be like this. Just simply pull that 38 into to be merged node, then it will form, this kind of structure. What is that? Single node at this moment, 0 keys. So since there are 0 keys, there is one pointer, but the problem is minimum keys should be 1, right? Then it will be violated. It is like now problem at internal node. Whenever while deleting in leaf, because of that the problem propagates to internal node, then how to solve it? First of all, borrowing from siblings. So we'll try to borrow from the siblings, but this internal node has a sibling which is having exactly minimum keys, then we can't go for borrowing. Then only thing is what? Pull the key from the parent. So we merge these two nodes and we pull the anchor. If I do that, you get like this, 6 and 10 and all the remaining keys of this right side, and you form 3 pointers. Do not worry, we have 3 children, we can adjust like this. 6 left is 1, 6 right is 7, 10's right is this 38, 39. So let's keep deleting so you understand. So always we are dealing with case number 1, you remember. Delete again whatever you want. So let's say delete 1. If I delete 1, insufficient keys, then go for borrowing, it will not work, then go for merging. Whenever you merge, then we have to merge these two nodes and we have to pull the anchor. When you do that, it will be 10, left is 6, 7, right side is 38, 39, correct? So again, now we have lot of keys. Delete 6, no problem. Delete 7, insufficient keys, then go for borrowing. Borrowing will work through the parent. So it will be like this. Mr. 38 will go here, Mr. 10 will come here, that's it. So it will be 38 and here 38 will be deleted. 38's left is 10, 38's right is 39. In that way we can do any number of deletions. Let's do deletion at 10. Insufficient keys in the resultant node, then transfer the keys from right side sibling or left side sibling, but insufficient keys in both of them, in this right sibling. Then what to do? We know it, merging. Whenever I merge, 38 will be pulled, the result will be like this. When 38 is pulled, 38, 39 and this empty node, right? This entire thing, these two will be merged and 38 will be pulled. Then in the root there is only 0 keys. So whenever there is a root, remember in this one, whenever you get a root with 0 keys, simply discard that root and decrease the number of levels. That is one thing you should do, because we can't go beyond that root, right? So we can't adjust. Example, root has insufficiency, we can't adjust it with next level because there is no next level. Simply we delete that level. So you get this 38, 39. Delete 38, no problem. Delete 39, Since your tree is empty, we stop it, nothing to do. So this is about deletions in B tree, especially we dealt with a case called deletion in leaf. Now we'll see how to delete keys from internal nodes. So far we have seen how to delete from leaves, right? Now we'll see how to delete from internal nodes. So for that I am taking a different tree. So that is order 5 tree. Of course, so the reason why I am taking order 5 is only to explain you in a different tree. That's it. So you can use old tree also, not a problem. In order 5 tree, I am assuming minimum key is 2, maximum key is 4. With this we are going to do that. Okay. So let's delete first some key value from this one, 20, 25, 30. So in this one, if I delete, example, whatever, you can take anything, 20. So the problem is, it's not like deletion in leaf. So when you lose this key, there are a lot of children. Again, maybe these children might have again subtrees and some more children. Then we should be careful, right? So then definitely we need an anchor here. That is one driving point. So because of that, what I do is, I try for alternative. So what is the alternative we can keep here, since this key value is 20, right? So always my strategy is I try for in order successor or in order predecessor. Always that element will be the right element. You see here, example, for 20 in order successor is 22, right? If you keep 22 here, but of course we are losing this 22 from leaf, we'll see that later. But if I keep it, then 22's left will be 10, 15. 22's right will be 24. Perfect. That's why. So what I want to say is, you can keep 22 here in the place of 20 if you delete 20. Now in the place of 20 we can also use 15, which is in order predecessor. If I keep 15 here, see, left side we have 10, which is smaller than 15, obvious, and right side elements are already, we know that, greater than 15 or equal to 15. So that's why it will work. Correct. So from now onwards, strategy, whenever we delete a key from internal node, blindly replace that key value first of all from first of all, which is in order successor, otherwise in order predecessor. Which one you want? Anything. So quite symmetric things, these two. Either we can pick in order predecessor, in order successor. As a student, you get this kind of question, that is, sir, if you don't tell us that whether it is in order successor or in order predecessor, in the exam if they give question, which one I have to pick? That's why there is no question from deletions, I can say, because there is ambiguity. That means anything in implementation can be taken. So they can't frame a question, right? If they frame a question, then go for in order predecessor and in order successor and evaluates the options. So if any option matches, tick it. If there is an option when in order predecessor is taken, if in order successor is taken, one more option is there, then definitely it is ambiguous. So multiple choices will be correct. They don't frame such questions. That is what our hope, right? So we hope that. Now in this one, from now onwards, I use in order predecessor. So here in order predecessor is 15. You keep it. Then your problem will be reduced to fresh problem, that is deletion in the leaf. So you know that how to delete from leaf, right? We use it. So how to delete from leaf? Simple. Whenever you delete from leaf, what happens? Minimum case may be violated. Here minimum keys are 2, but you have only one key. We should handle. Start from the fresh, right? So in that one, how to do the things now? First of all, in deletion in leaf, step number 1, borrow from the neighbor or sibling. Since this sibling doesn't have sufficient keys, correct, then we have to go for merging. So this is the idea. So let me merge 10, 22, 24 into one key, 10, 22, 24. But along with that, already I told you, whenever you merge, we pull 15 also. That's why it will become 10, 15, 22, 24. So here it would be 10, 15, 22, 24 is the final answer. 2 keys, 3 pointers, right? So in that way, so finally we stop this, right? Now we'll see one more example. This time I delete 48. So again, case number 2, deletion from internal node. If I delete 48, then first of all replace it, and now remove it and go for in order predecessor. What is the in order predecessor? In order predecessor of 48 is dash 47, otherwise in order successor is 50. Anything you can take. Let me take in order predecessor 47, then remove from here. But if I remove from here, the problem is this doesn't have sufficient keys. That's okay, like we know how to handle it. Whenever you delete from leaf, if that node doesn't have sufficient keys after deletion, what you do? Go for borrowing. Now here borrowing will work. So borrow through parent, right? That means you have to push the keys through parent. So 50 goes here, we know that, right? 50 comes here and 47 comes here. In that way 50 will be moved to this side. So it's like a rotation, correct? So we remove 50. Now perfect, see 50 is left, 50 is right. In that way we handle various deletions in internal nodes. We'll continue one more thing. Let's delete one more time. Let's say if I delete 50. If I delete 50, then again insufficient keys. Step number 1, identify the in-order predecessor. What is in-order predecessor for 50? So in-order predecessor for 50 is 47, write 47 and delete 47. That's it. If you delete 47, it will become deletion from leaf. Whenever you do deletion from leaf, what can happen? Insufficiency. Here you got that insufficiency because minimum number of keys should be 2, but you have only 1. Step number 1, borrow from your neighbors, right? So we have left sibling, right sibling. You can take either key from left sibling or right sibling. Let's try left sibling. But if you remove a key from left sibling, then minimum key condition will be violated. That's why we can't take here, we can't take here. Whenever you can't take the keys from siblings, then we have to go for merging. So I am doing the merging now. So did you remember how to merge? So either merge these two or these two. Let me choose this one. I am merging these two. Whenever I merge these two, we have to pull the key. Already I told you so many times that in B tree, whenever you merge the nodes, the anchor should be pulled into it. So 47 will come here and the resultant node will become 45, 47, 52, 54 and one pointer. That's it. 44's left, 42, 43. 44's right is 45, 47, 52, 54. When you do that, so you get problem at internal node C. So here again this internal node doesn't have sufficient keys. Now don't deal this case with deletion from internal node. Whenever your deletion is from internal node, that is separate. Now this is different one. How it is different? I was adjusting leaf at that time, so I pulled one key from internal node. When I pull a key from internal node, then your internal node might have insufficient keys. When you have that problem, we should deal it separately. So why we should deal separately, I will tell you. Here actually the key and pointers are properly adjusted. That means we have one key and two pointers, correct? But if you remember, if the problem is deletion in internal node, then example, let's postpone this problem. Example, the problem is deletion from internal node, then you are just losing the key but you have pointers. At that time we should deal in a separate way. I already explained that, correct? So this is something 17, right? Now, so that's not the case. Our case is different. We have a internal node with insufficient keys. So how to deal this one? Already when we discussed leaf node deletion, key in the leaf node deletion, we have discussed it. Let me repeat it. Whenever you are deleting some keys from leaf nodes, the error may propagate to internal node. At that time, how to handle it is borrow from the left sibling or right sibling. So borrow from the left sibling, but left sibling doesn't have sufficient keys. Then try to borrow from the right subtree. When you borrow from the right subtree, then you should be careful. 70. So whenever you want to move 70 to this side, so all the children also has to be moved. Correct? So I am going to plan it. What we do is we delete 70 and we keep 70 here. Remember one thing, whenever you borrow some keys to one place to another place, we have to use the anchor. So this 70 comes here first of all and this 60 comes here. So this is the way we do. When you move it, now see this only this child will be moved to this side. See 60's right will be 65, 69. Try to understand. When you move one key here, then the resultant keys will be 2 and they will need only 3 pointers. This one, this one, this one. Then this one is extra pointer should be moved to this side. And the key movement is through the parent. That means this key should be moved here, this key should be moved here. In that way we can move. Let me repeat this kind of things one more time so that you understand. So let's do one more time. Do deletion in internal node again. This time we'll pick something, let's say 25. If I delete 25, deletion from internal node, how to do it? Step number 1, go for, see this time I am not borrowing from the left sibling or right sibling. Don't do that. The reason, we have here pointers, so definitely one key is required. So at that time we don't move the keys. So what we do is we try to replace it with in order predecessor or in order successor. That is the first rule of deletion from internal node. So go for in order successor or in order predecessor. So when you do that, in order predecessor has sufficient keys, we keep it. Okay. So 24 and I move it. Successful. Nothing to do. So now you don't require to handle deletion in leaf, correct? Because it has sufficient keys. Let's do it again. Delete 24. If I delete 24, then again in order predecessor 22 will be replaced. Delete 22, then replace with in order predecessor, which is 15. First you write it blindly, then think about it, remaining thing. When you replace here to here, this leaf might have insufficient keys. How to handle it? It is like something deletion from the leaf. How you handle the deletion from leaf? Let's revise. Whenever you have deletion from leaf and there is a insufficient keys problem, then borrow from the left sibling or right sibling. If it won't work, then go for merging. When you do that merging process, what can happen? The error may propagate to next level because you are pulling up some key to the downside. When you do that, your internal node will have less number of keys. At that time, minimum condition might be violated. At that time, what to do? Then do the same thing like borrowing. From now onwards, at that time you have to go for borrowing. Borrow from left sibling or right sibling. Sir, if it is not possible, that means your internal node, left sibling and right sibling, both are not having sufficient keys. They have exactly minimum keys. Then what to do? Simple, same merging. At that time we merge. Let's do that. So here this key is deleted. Step number 1. Whenever deletion in leaf happens, we have to go for borrowing, correct? So borrow 26, but through the parent. So 26 goes here, we know that, and 15 comes here. So far good, 26 should be deleted. But to borrow, this kind of problems arises when you borrow from a node which has just minimum keys. So it's wrong. Don't ever do that, right? So it was what? Something 20. Now let's see the deletion. So when you delete here from this leaf, then we have to borrow from the right sibling. But since this right sibling has exactly minimum number of keys, what to do then? Only merging. Let's merge these two. When I merge, we have to pull this key. When you pull, probably this internal node will have insufficient keys. That we will deal later. First of all, 20 will be pulled down. It will be 10, 20, 26, 28. Correct? That's it. One key, 2 pointers. 30 is left, 30 is right. Let me read right. So it would be 10, 20, 26, 28. Right? Now, let's deal this case. This internal node has insufficient keys. Then what to do? Go for borrowing. To borrow, this internal node doesn't have sufficient keys. It is exactly having minimum keys. So what to do then? Then try left side. There is no left side. Then go for merging. So same recursive process. So merge. So when you merge, we should be careful. You will form. Whenever you merge any two nodes, we have to pull the anchor. Let's show here 30 and I pull the anchor 40 and 44 and 60. When you do that, you get exactly 5 pointers. I will show that 5 children. 30 is left as it is. 10, 20, 26, 28. 40 is 30, 40 middle. 30 and 40 middle. I can say 30 is right. 35, 37. Definitely it will be say 40 is left. That's why it's perfect position for this node. Now in between 40, 44, you see 40 is left. 40 is right. 44 is left. Since it is 44 is left and 40 is right. That's why it will work here. So that's why it is 42 and 43. Now 44 is right as it is 45 and 47, and this one is 60 is right is 65, 69. Of course here 45, 47, 52, 54 also, not a problem. So this is what happens here when you merge. Then in the next level you will be only 70, right? You will be having only 70, and 70 is right will be as it is 90, 100. That tree will not be disturbed. This is, let's say, T, this entire thing. So we write here T. Okay. In that way, deletions in B tree will work. Okay. We covered all the cases. Let me summarize. Case number 1, deletion in leaf node. Whenever you delete from leaf, let's say already that node has more than sufficient keys, then simply delete and keep quiet. Now, if it doesn't have sufficient keys, that means it has exactly minimum number of keys. When you delete, example here, if you delete, then what to do? Borrow from left sibling or right sibling, whatever is convenient. If you don't get chance to borrow from left or right, we know the reason, then we merge. When you merge, we pull down a key from next level. When you do that, that will become definitely internal node. That internal node will lose one key, then it will have, it might have insufficient keys. Whenever it gets insufficient keys, then borrow from left child or right child. Already I told you how to do that. Then you borrow that key through the parent. Of course, I explained you the process, you follow that and borrow from left sibling or right sibling. If left sibling and right sibling also has exactly minimum number of keys, merge. When you merge, we pull down one more key from the next level. So because of that, same thing might happen and we repeat the process. Borrow or merge, borrow or merge. This is a story about deleting from the leaf. Now second thing, deleting from internal node. Carefully. First step, when you delete from internal node, whatever the key, example this one, immediately we have to replace that position for any cost. From where we have to replace this position value with either in order predecessor or in order successor. Only go for one thing. What is the reason? So because finding in order predecessor or in order successor will be time consuming, because we have to traverse entire height of the tree. Then lot of blocks we have to visit, isn't it? So it takes lot of time. That's why. So but we don't have option in this algorithm. So we go for in order predecessor and whatever it is. Otherwise you do one thing, always go for in order successor. Don't try to go for in order predecessor and in order successor. The reason, it is having lot of block transfers, right? So you might have this question in your mind, sir, if I go for in order predecessor and that node has exactly minimum number of keys, but in order successor has lot of keys, then why don't we prefer in order successor? But first of all, for that we have to go for in order successor, right? When you go for in order successor, in that process you will be visiting lot of blocks. For that, there is a lot of computation. Every block you want to visit, that should be transferred to main memory and it should be processed. It takes lot of time. That's why, to avoid that computational expensiveness, what we do is blindly we go for in order predecessor. Whatever it is, if it doesn't have sufficient keys also we delete. Then we handle the remaining case as deleting from the leaf. Otherwise you fix in order successor always. Whenever you remove in order successor from the leaf, then remaining thing is, example that node doesn't have sufficient keys, go for a case called deletion from the leaf. You know the story about deletion from the leaf. So whatever you want to do when you delete a key from the leaf, you do all that things, don't worry. So this is a process of deleting from B tree. Okay. Now in this example, I would like to discuss about a case where you have borrowing from internal node to another internal node. Okay, so that situation arises. Actually we discussed it, but one more time I would like to teach that. So example, here you are deleting k5, otherwise let's delete k1. When I delete k1, see this tree's order details, order 5 minimum, let's say. So it's not order 5, let's take order 10. In order 10 B tree, minimum keys are 4 and maximum 9. For this one, see now minimum keys condition is violated. Then what we do? Deletion in leaf. Recall. First step, borrow from the siblings, correct? So to borrow from the sibling, assume that let's say C has exactly minimum keys, and now E also has exactly 4 keys, which is minimum. Then we can't go for borrowing. Then only thing is merging. How to merge? First of all, the anchor is 50. 50 should be pulled down, and K2, K3, K4 and remaining 4 keys will be merged. K2, K3, K4 and that 50 and K5, K6, K7, K8. All these keys will be merged into one node, right? Now see how many keys we formed finally. 1, 2, 3, 4, 5, 6, 7, 8. Maximum condition will not be violated, don't worry. So 1, 2, 3 keys, 1, 2, 3, 4 pointers, perfect. But the only problem is this node has insufficient keys. I would like to discuss this case. So whenever you have insufficient keys in internal node, it's because of you pull down one key at that time. What we do? Again borrowing, that's it. So this is now internal node borrowing. Whenever do internal node borrowing, how to do is same thing. So finally I would like to send this 60 to this side. I can't send directly because 55 is left, cannot be 60, correct? That's why we move like this, 60 to here. Mr. 60, you just go here. Okay, now Mr. 55, you come here. Now because of that, one extra pointer we can accommodate, correct or not? So here you see 1, 2, 3, 4 keys, 1, 2, 3, 4 nodes. The fifth node, that fifth node you remember we can keep. What is that? I will tell you. Since you have removed one key from here, then remaining keys are 4 and that 4 keys are pointing to these 5 boxes. So this is the extra box. So that extra box which is F is going to come here. That is what I want to say. Always we do this process. Automatically all the keys in this F node will be smaller than 60 because 60 was here, right? So 60 definitely these values are smaller than 60. We know that. So this is the borrowing step. Okay. Let's see this gate question. In the index allocation scheme, the maximum possible size of the file depends on what? So if you see the option, size of the blocks and size of the address of the blocks, here number of blocks used for the index and the size of the blocks. If you see option C, size of the blocks and the total number of blocks used for the index and the size of the address of the block. So option C is right. I will tell you what is the reason for that. Example, take one parameter called size of the block. This size of the block is very huge. Example, let's say you have very big block, then you can accommodate lot of pointers, then you can have, you can index a very big file, correct? So block size is definitely influencing, but only block size is not sufficient. That means, if you have very big block, it doesn't mean that you can accommodate any file size. The reason, even with the smaller blocks also I can do the same. That means only block size is not going to decide the maximum file size. Example, your block size is 1024 and assume that in that you can keep, let's say, 50 pointers. So you can index a file of 50 records for simplicity. Only one block I am taking. Now rather than 1024, if I take 512 size blocks, then I can take, let's say, multiple like this. By taking multiple such blocks, then I can index bigger file than this one, correct? So what I want to say is only block size is not going to decide. How many number of blocks you are taking also important. That's why, so block size is one thing. Second one, number of blocks also going to influence. There is one more parameter. If you see in the option B, number of blocks used for the index and size of the blocks, correct? If you see the option C, number of blocks, size of the block, number of blocks and the size of the address of the block. How size of the address of the block is going to influence, we'll see. Let's fix, to understand the third parameter, let's fix this one, block size and number of blocks. Let's say I have only 2 blocks. Okay, let me fix it. 2 blocks, each of size, let's say 1024 bytes. Okay, then if my block pointer size is, let's say, smaller, then what can I do? More addresses I can, otherwise more block pointers I can accommodate in one block, correct? So that I can index a bigger file. What I want to say is, if your block size is fixed and number of blocks also fixed, then in that scenario, if your block pointer size is, let's say, one case is 16 bytes, second case is block pointer size is 32 bytes. Then if I choose block pointer size 16 bytes, then what happens? Then more block pointers I can accommodate in one block if you compare with this block pointer size. If that is the case, then more block pointers whenever I accommodate, bigger file I can index. That's why this block pointer size is also going to influence your scenario, right? That's why block pointer size is one important. Second one, block size is also important. Third one, number of blocks. Everything matters, right? So this is about, this problem. That's why I can say that all these 3 parameters are going to influence your maximum file size. That's why size of the block, number of that blocks, and third one, how many block pointers you can keep in one block. That means it depends on the, of course, block pointer size. So block pointer size is also going to be matter. Okay, let's see this gate question which is asked in 2009 paper. The following key values are inserted into B plus tree in which order of the internal node is 3, remember it, and that of the leaf nodes is 2. So there are 2 orders, leaf order, internal node order, in the sequence given below. The order of internal node is C. In the problem itself they mentioned what is the order of internal node. We'll read it. The order of internal node is the maximum number of tree pointers in each node. So yes, it is quite obvious thing for us, because in the same way we also defined our B plus tree. So in each node. Second one, and the order of the leaf nodes is the maximum number of data items that can be stored in it. Let's focus on these 2 points. So order of internal node is nothing but so maximum number of tree pointers, correct? So here order is 3, then maximum number of tree pointers are 3 in internal node. So how many keys we can keep? Only 2. That's why finally that is important for us, right? So in internal node, maximum keys equal to 2. Now let's read internal leaf definition. Order of the leaf nodes is the maximum number of data items that can be stored. How many maximum? So since order is 2, then maximum number of data items we can store is only 2. That is the way it is defined. So data items are here keys, right? We know that in B plus tree, leaf node contains keys comma record pointer. That's why here data items are nothing but keys. So that keys are order exactly equal to order. So what is the order? 2. So maximum keys are 2. That is the way it is defined. Key 1, key 2. Let's say in that way. So finally I can say that maximum keys in leaf equal to 2. Right? So if you have doubt, read it again. Order of the leaf nodes is the maximum number of data items you can store. If I store 2, then that is the order. Example, maximum you can store 2, then it is order. That is the way it is defined. Yes, we know that order is 2, so it is 2. Next, in such B plus tree, initially empty, and we are inserting 10, 3, 6, 8, 4, 2, 1, then how many? Maximum number of times leaf nodes. You should be, you should be clever and you should be attentive. That means you should understand the question clearly. We have to identify the maximum number of times leaf nodes would get split. Be careful. So remember it. Maximum keys are anywhere 2 would get split up as the result of these insertions. Let's do it. So first we insert 10 in new node, right? No node split so far. So insert 3. So we know that we insert them in ascending order, then 3 will join this node. So far node splits. Then 6 will come. Whenever 6 comes, your resulting tree will be like this: 3, 6, 10, but maximum condition is violated. Then we have to do what? Node split. So here I assume that node splitting algorithm is used, correct? Why? Because node splitting algorithm, one reason is node splitting algorithm gives you maximum number of splits. That is one reason. Second one, generally if nothing is mentioned, usually we go for node splitting, okay? But especially I have a strong point why I am using node splitting. Question is for maximum number of node splits. If you do redistribution, you are adjusting the keys. When you adjust the keys, then number of node splits will be reduced. That's why don't go for that. So I seriously go for node splitting because I know that I want maximum number of node splits. Then here you are going to get the node split. What is the idea in B plus tree? Recall. So we divide your keys into 2 parts. So one is 3, 6, second one 10. Otherwise 3 here, 6, 10 here. Remember one thing. Middle element is going to be anchor first of all, right? So 6 here and 6 left something, 6 right something. There are actually 2 ways. So what we did is we divided our keys in a way that all the greater than or equal to one side, less than other side. Already, at that time I told you that this is not compulsory. Why left to side strictly less than? Why not less than or equal to here and greater here? Yes, it is also possible. If that is the way, if you define your B plus tree, then what happens is, so 3, 6 we keep in the algorithm. So my node splitting algorithm can keep 3, 6 here and 10 here. That is one way. Second one is 3 here and 6, 10 here. Whenever I use this model, I am assuming that anchor's left side is strictly less than and anchor's right side is greater than or equal to. If I use this division, then anchor's left side is less than or equal to, right side greater than 10. So both are equally possible. Then anything I can choose. What our question is what? Finding maximum number of data. Maximum number of splits, correct? So for that, what we do is, first of all we go with this and we count the number of splits. After that we go with this and we find out the number of splits. After that we go for better choice. That means maximum. Let's do this time. Case number 1. So left side strictly less than, right side greater than or equal to. Let's follow this model first. Then it would be resultant tree will be 6, left side 3, right side 6, 10, right? Next, insert 8. So here 8 will come here, then again it would lead to one more node split, correct? So let's convert the tree. 6 here, 6 left is 3, 6 right is, see, so here split, right? How to do the splitting? Take the middle key, it will go to the next level because of the 3 nodes will be created, we know that. So one is 6, second one 8 10. So 8 10 here and 6 here. I am following this condition. So far tree is like this, 6 8 3 6 8 10. Now 4, when I insert 4, so 4 will come to, see, search for 4 first. 6, I mean 4 is less than 6, right? So it will come here. So answer will be here 3 comma 4. Now so far number of node splits, let me count, 1 plus here 1. Now here next time here you got split, one more split, remember it. Now whenever you insert 4 there is no node split. Go to 2, when you insert 2, so again there is a node split, maximum keys can be 2 only. Then we will send 3 up, let's do it. If I send 3 up, then it would be 3, say 6 comma 8. Then it will form, 4 boxes, correct? 4 pointers. So these are the pointers. 3's left will be, the split model, when 3 sent up, 2 will be one side, 3 4 will be other side. 2 is here, 3 4 is this side, right? Now 6 is as it is, 8 comma 10. So one more split. So far we have seen 3 splits, correct? Now continue. But before that, this is not a valid B plus tree. Internal node is having now more than maximum, we have to split it again, but don't count it because it is not leaf split. So 6 will go up, we know that, right? Let's show here. 6 will go here and 6 left will be 3 and 6 right will be 8. That's it. We don't copy 6 again. So perfect. Now this is B plus tree. Now add 1. If I add 1, happily it will sit here. Only 3 splits. Now we see the second case. Okay. First of all, we start with again 10. This time idea is left side less than or equal to right side greater than. Remember it. Next 3 comma 10. No problem so far. 3 6 10 next time because of 6. 3 6 10. So 3 insertions. Now node split. Count it. So this is case 1. This is case 2. We got one split. Now send 6 up. Correct? Less than or equal to this side. 3 6 this side. 10 this side. Now insert next element, which is nothing but 8. Then 8 will, idea, right? So greater element this side, 8 here, no split. Then 4. So 4 will come here. When 4 comes here, it would be, split again. Count it first of all. Then lift 4 up. When you lift 4 up, it would be like this, 4 comma 6. 4's left will be 3 comma 4. 4's between 4 6 it will be 6 and right side will be 8 comma 10. Now insert 2. When I insert 2, then again there is a node split. Count it. Plus 1, right? So when I do that count, then what happens? So 3 will be lifted up. 3 4 6 in one level. 3 is left. 3 4 middle and 4 6 middle. 6 right. So here we know that 2 3 will be this side in this model. 4 will be here and here 6. Here 8 comma 10. Now we have to further split, correct? But it is internal node split. We should not count it. You get like this. So 4, 4's left 3, 4's right 6. So 3's left is 2 3, 3's right will be 4 and 6 left will be 6, 6 right will be 8 comma 10. Now 1 comes. When 1 comes, then again 1 will go this side. See, 1 2 3. Then it will split the leaf node again. So one more. So finally, if I follow this method, we are getting 4 splits. In the previous case, only 3. Now the question, because they did not mention which method we should follow, then we should consider both of them and we should go for best possibility, because I want to know the maximum number of times leaf nodes would get split. So for that, definitely answer is 4. Right? Let's see this problem which is asked in GATE 2007 paper. The order of a leaf node in B plus tree is the maximum number of value comma data record pointer pairs it can hold. So that means, so you have a B plus tree leaf node, its order is defined like this. How many data comma record pointers you can hold, that is order. If your if your leaf nodes order is P, then maximum number of pairs we can hold is P. So each pair is having a value comma data record pointer. That means, so I can say that here you have p values comma p data record pointer. This is a maximum situation. So finally, in the worst situation or in maximum situation, you will have these many entries in your node, followed by, so generally in B plus tree, leaf is connected to left node and right node. Then only, when leaves are connected, we can efficiently use this B plus tree for range query. That is the advantage over, generally B plus tree gets advantage over B tree only for this reason, right? So that's why. But the question, sir, should I have two pointers or one pointer? There are two implementations of your B plus tree. In B plus tree, so your leaves can be connected in a single linked list way like this. Every node is connected to the right node, next node. If you do that also, we can do the range queries. Second thing, you can have another implementation where, so every node will have two pointers. One is for left predecessor, otherwise left node, right node. So here also I maintain left node pointer and right node pointer. So here left node pointer, right node pointer. Then it will form double linked list. Then each node effectively will have two extra pointers. So let me use that one, but it is ambiguous here. Should I use one pointer or two pointers? Then what to do, sir? What you do is solve this problem with two pointers and one pointer. But surprisingly and fortunately, so both answers, that means both cases will lead to same option. So we don't have any problem. Let me take two. You do one thing, take one and solve this problem and you get same answer. So that's quite lucky thing for us. Now if you ask me, so students ask this question, sir, finally you tell me, should I take two or one? Anything is okay, right? But you should go with the options. That means based on the option you should decide. Now let me take, that's why 2. So assume that what are you going to do finally? You remember one thing, in B trees and B plus trees, your logical node is going to exactly fit in physical block. Such a way we are going to arrange our order. So you tell me what should be the order so that it will exactly fit into this 1k blocks, right? So block size is 1k, that means 1024 bytes. So whatever the order you fix p, that should be such a way that these p values and p data record pointers plus 2, which are going to be maximum, that entire thing, their size should be less than or equal to 1024. If it is more than that, how can you accommodate in one block? If you keep a data node, if you keep any leaf node or internal node of any B tree or B plus tree in, multiple blocks, what happens is unnecessarily to access one logical node, multiple blocks we have to access, and usually in B trees this node is having collectively similar information. So definitely when you search, when you do access of this one, then there is a high chance that you access all these keys or whatever. So that's why all that logical information should be in one block so that we can reduce the number of block transfers. That's why remember one thing, a logical node always in B tree will exactly go to one block. That's why, so this capacity should not exceed 1024 bytes. Then if you have p values, key values, how much size they occupy p into, what is the key size? In the problem it is mentioned that key size is 9 bytes long, right? So remember it. Plus, now how many data record pointers you are going to store? P. What is each size? Read it. So you will understand that here block pointer is 6 bytes and data record pointer is 7 bytes. That's why it is 7. Plus you are going to store two extra pointers. What are they? They are especially pointers to the nodes, correct? So each node is nothing but a tree pointer, correct? It is going to point to the next node in the tree. These are all, I can say that, blocks, correct, in the implementation. So each pointer is going to point to the another block. So two block pointers we are going to use finally. That is the difference between data record pointer and block pointer. Already I explained so many times what is the difference between block pointer and data record pointer. Here especially these two are block pointers. That's why, what is the block pointer size? So block pointer size is 6 bytes. So this entire thing should be less than or equal to 1024. Let's simplify it. So here, how many? This one 9p here, and so this one p into 9 plus p into 7 plus 2 into 6. Let's simplify. 9p plus 7p plus 12 less than or equal to 1024. Then it would become, let me erase here, 16p plus 12 less than or equal to 1024. So 16p less than or equal to 1012. P should be less than or equal to 1012 by 16. If you simplify, 2 8s are 2 506. So 2 4s are 253s. So 4 6 are 24, 13 4 3s are 63 point something, whatever. So P less than or equal to 63 point something, that means 63. So option A is correct. In the place of 2 pointers, if you take 1 also, you get same answer. Okay. Now we'll see one more gate question. A B tree of order 4 is built from scratch. That means from starting by 10 successive insertions. They did not mention the numbers. What is the maximum number of node splitting operations that may take place? So what we do is, so we try to insert number such a way that that will always lead to maximum number of splits. We'll try that. First of all, I start with 10. And one more thing, since it is order 4, then maximum keys a node can accommodate only 4 minus 1, 3. So let's insert 10, then 20, then 30, now 40. So when you add 40 to this existing node, then split occurs, correct? This is the first point. So whoever inserts, whatever the way they insert, so no one can get split before inserting the fourth element, correct? So after inserting fourth element, you get the split. Now you have two choices to lift the anchor up, that means middle node, so middle value 10, 20, 30, 40. Either you can take 20 because this is middle, even 30 also middle. Middle means median. There are two medians. What to do? Theoretically speaking, there is no distinction between them. Anything can be a choice. Then what to do? Let's take 1. And you slowly understand that it's symmetric. Like if you take 30 or 20, you are not going to get any advantage. The reason the numbers are in your hand. You can plan the elements such a way that you can always lead to maximum number of splits in any structure. That's why let me take always, the number which is left side in two medians, left side I am taking. So 20 will be lifted up, and my suggestion is, if you have curiosity to know that what happens if you lift 30 up, then you do that. Okay, so I'm trying this 20 and you try this one. Now 20 and left side is 10, right side 30, 40. So my common sense says that this time onwards try to fill values such a way that this will be quickly filled, correct? Because if you try this one, it is already having only one key, but here you have two keys. Which one is better? Which one will be quickly splitted? This one. That's why I will try to insert my value such a way that they will come here. So for that, target is 10, 20, 30, 40. I keep 50. So it will land here. Then I insert 60. Then it will again land here. So now split. Correct? So this is the best way of splitting the tree. So here, one more split. Let me count the number of splits. So far 2 splits. Now what is our strategy? Whenever we get split, what to do? Then left side element to be picked out of the medians. So this is leftmost. So 40 will be picked up. When you pick 40 up, then 40 will go to this level. We know the insertions, right? Here it would be 30 and it would be 50, 60 so far. Now insert 70. The target is what? Always try to fill in a box which is having more keys. So that's why we try to insert 70. Then 80. One more split. Correct? So we tried 70, after that 80. Now one more split, we are going to lift 60 up. When you lift 60 up, let me count the split number, 3 splits, 20. So 60 will go to the next level, 20, 40, 60. 20 is left, 10, 20, 40 in between, 30, and 40, 60 in between, 50, 60 is right will be 70 and 80. Now we have two more choices. So again I will try here itself, that's why 90, then 100, so that always I am trying to fill a box which is maximum filled, correct? 70, 80, 90, 100. Now you tell me one more split, fourth split. Because of that 80 will be lifted up. When you lift 80 up, what happens? This 80 comes here, correct? Remember it. Now, so I don't adjust it, but I will realize that. So here split, because of that this root will have now 4 keys. Because of that we have to split this also. The question is what? Maximum number of node splitting operations. That's it. We don't need to adjust because we have only 2 minutes of time. Why to waste? Then one more split, correct? So finally number of splits are 1, 2, 3, 4, 5. So we can know, I mean, identify that. Split at 40. Then next time, so we add, so you will have 30, 40, then 50, 60, split at 60. Then we add 70, 80, split at 80, correct? One more split, right? How many splits finally? 3. Then at 100, one more split. Because of that, you get 4 and one root split. So one more, 5. So answer is just 5. Okay.